You still have the opportunities, but the most important thing is you need to understand what we are doing. But actually, I'm satisfied with your performance. You guys show me that most of you can understand what I'm talking about. So actually, it's okay. Okay, unit. Usually a big issue for you guys, right? You know. Yeah, but you don't. No, it's no. The thing is, you should not think that's a problem to write down a unit. It's supposed to be one of the important parts of your answer. Okay. You need a habit. You need to become, this is a habit.
So because
reduce the angle.
sounds like I'm in karaoke right now. I should sing a song. Okay. Because I think most of you can follow, you understand, but maybe you make a mistake, you forgot the unit, or you forgot 2 pi, you forgot something. Okay, that happened.
That's fine. I just get rid of it. I am satisfied with my teaching because I think all of you can understand. Most of you can understand. Like I think like 80% of students understand what I'm doing here. So I can just continue. I can continue and go to next step. Okay. But before we start, there's something I need to do is I need to summarize what we did for the last 2 weeks, okay? A summary, which means maybe you can find equations. You can find equations here. I posted on the website as well, and you can get through it. Those most important equations, okay? For your final exam, you will use these equations again and again. Okay. As usual, I'm trying to describe the voltage and the current on a high frequency transmission line. At the end of this transmission line, I defined the coordinate z equals to 0. Okay? Okay? I'm doing the summary. I try to organize all the most important equations we have learned in chapter 2. So the voltage is a function of position z. It is V0 plus, I don't know what it is. This is the beginning, the magnitude of positive voltage is V0 plus, usually we will have this value at the beginning. This is kind of your question. Okay, the start of your question. Multiply exponential. If this transmission line, it is a lossless transmission line, because your teacher is very kind. I ask you, lossless, thank you. Lossless transmission line. So we want the simplest case of the transmission line, which is lossless. So it is minus J beta Z. What is beta? Beta is the imaginary part of the propagational constant, or maybe you can say it is K of the transmission line. Okay, so beta, it is one of the parameters of the high frequency transmission line. Okay, and the Z is the position where it is. Where it is, Z means where it is, okay? Plus V0 minus exponential positive J beta Z, and the current equals to I0 plus multiply exponential J beta Z plus V0 I, yes.
That's correct.
Now you understand, right? It's not so hard, right? So I will write down the rest of the part. At the beginning, we don't know the magnitude of V0 plus, V0 minus, I0 plus, and I0 minus. And we are looking for a relationship. What are the relationship of these four magnitudes? Okay, so the first of all, we need to define a new parameter. So we define. First of all, we define gamma. It is a reflection coefficient, and more, because this is a reflection coefficient at Z equal to 0. Maybe I'm talking about more than what you can see in POSA, but I'm talking about a more general case, okay? So this is at the Z0, I will have the reflection coefficient at the point here. Okay, the reflection coefficient at Z equals 0, we have the definition of this guy. It means the voltage, reverse the voltage at this point, and the forwarding voltage at this point. I find out the ratio between these two parts. The ratio of this one over this one. This is the reflection coefficient. And I want to find out what is the reflection coefficient at this point. It means Z equals to 0. So you can write down, okay, I just write down everything. Okay, and Z equals to 0, so I can write down 0 here. Exponential to the power 0 equals to 1, right? So you obtain that the result is, this is the definition, equals to V0 minus over Z0 plus This is the reflection coefficient at z equals to 0. Okay? Similarly, you can also, this is talking about the next part, okay? So try to understand. I also want to, what is the refraction coefficient at any position? Okay? According to my definition, I can write down gamma reflection coefficient at any position is V0 minus multiply J plus J beta Z exponential to the power J beta Z over the positive part. Okay, reversed forward. Okay, so it is the ratio between these two voltages. It is a reflection coefficient. So it is a function of, you can see that, they are the same, right? So for this part, it is here. So now you can simplify the equation as positive J 2 beta Z. This is a general form of reflection coefficient at any position. You can put any Z there, okay? Z can equal to something else. So you can see there is a phase change. The phase is here, right? Beta Z, it is a phase depending on your position. Remember, the phase equals to omega t minus beta Z or omega t plus beta Z. This is a phase. You have a contribution from time. You have a contribution from your distance. So if you don't look at the time, you're going to look at the contribution from time. You look at only the distance, your space. Beta Z is your phase shift. Okay? So see that? They are twice of your beta Z. You can see the phase of your reflection coefficient is changing according to the twice of the beta Z. Because you can think like, okay, you go there, you come back twice of the position, right? This is new. This equation is new here. Okay? I didn't mention that before, right? Maybe a little bit, but I formally write down, officially write this down. Okay. This is important. Moreover, let's do something more. So, also, I'm talking about a new definition. This is the first new definition. Another new definition about the relationship of these four parameters magnitude. These four magnitude is we define characteristic impedance Z0. It is the ratio of the positive voltage, the magnitude of the positive voltage over the magnitude of the positive current, and also equals to the minus V0 minus I0 minus. Okay. These two new definition can simplify our original voltage and current. We can simplify these two equations by using these two definition, or we say relationship, of these four magnitudes. right? Okay, so what can we obtain? We can obtain the new voltage is still V0 plus multiply exponential minus J beta Z plus V gamma 0, the reflection coefficient, it is a ratio between negative to positive voltage, right? So it becomes new form. Okay, this is an important summary. How about our I? This is a beginning, and this is after you have these two definitions, you can write down it is V0 plus Z0 exponential minus J beta L, and minus because of here gamma 0 V0 plus Z0 exponential J beta. Okay? Well, we did this before, right? But I write it down again because it is important. Actually, I think that this is not only the second time, it's more than twice. Write down again, because it is important. Okay, what else? I'm telling you that it is the voltage and current reflection coefficient everywhere, right? Where it is. Maybe we can try, what we want is, what is the voltage or current or reflection coefficient or new impedance at the other end of the transmission line? What are the functions of those values? Okay, so something we need to know is we need to know how long the transmission line is. If we define some variable value of the length of the transmission line, we call that L, small l, the transmission line. L is always the positive value. It means the physical length of the transmission line, right? But the position of here, the Z here, it is become negative because we define here is 0, right? So the left part is the negative. So and here we will find that Z equals to minus L at the other end of the transmission line. Okay, no problem, right? So according to this small definition, we can change these equations just from Z to minus L for everywhere. I'm still writing L here because it is the component, it's a function of L, right? But for here, now I change negative to positive, I change negative to positive. I change positive to negative from Z to minus L. Makes sense, right? So this is our new equations. Okay, what else? we have the equation of voltage, current, everywhere on this transmission line. We have the reflection coefficient, the function of reflection coefficient is anywhere on this transmission line, right? And last week, we did define something important. It is, remember, I just write down the result. The reflection coefficient at this point equals to ZL minus Z0, ZL plus Z0, according to some calculation. We did that before. Okay, if you forget, maybe you can follow, go back to check my video, okay? This is one of the important equations. You will use it very often in the future or in the past, okay? This is one of the things. I consider owning the ZL, and I consider owning the characteristic impedance of this transmission line. Forgot to write down. There's a new definition here. So my transmission line has a new parameter here, right? So what is the reflection coefficient at Z equals 0? You can directly write down this one, because how long it is doesn't matter. The length of the transmission line doesn't matter. Understand? Because I'm trying to calculate the reflection coefficient at Z equal to 0, so it doesn't matter it is long or short. Okay? So you will always have this result of the reflection coefficient at Z equals to 0, or you can say L equals to 0. But L Z equals 0 doesn't make sense, right? If there is a transmission line and that has a characteristic impedance Z0, doesn't make sense. I'm talking about the position, okay, at this position. So L doesn't matter. Only matter is Z0. Only matter is what is the load impedance. Okay? So one of the important equations here. Okay, this is the first one. And there is another important equation. We will use that many times here. So today, I'm writing down here, okay? The most important thing today, we are trying to deal with the result we derived last week. Z in at the impedance at anywhere. What is the input impedance at any position on my high frequency transmission line? Okay. First of all, you can go back to see that what is a Z in at Z equals to 0 or L equals to 0. What is this one? Z equals to, if there is no transmission line, the input impedance at here, look at this direction, Z in at 0 equals to ZL. Okay? No problem, right? How about this one? If there is a transmission line, what we are trying to get is what is the input impedance at somewhere here, which means my impedance will change. Why? Look at that. Your voltage is changing according to your position. Your current is changing according to your position, right? So your impedance is changing according to your position, right? Makes sense? But what can be a constant? Which parameter is a constant? Characteristic impedance. The characteristic impedance on the transmission line is always the same for a uniform transmission line, which means the ratio between them are the same. But doesn't mean the total voltage and the total current is the same. And the input impedance is changing. Okay, because the total voltage is changing, total current is changing, of course. The definition of Z in L is the voltage L over the current L. Every voltage, including the positive and the negative, the forwarding and reversed voltage, and forward and reverse current. Okay, so it is a function of position, and this is important. Okay. If you are not in the field of microwave engineering, you feel like this is ridiculous. The impedance changing according to different lengths, different position. But you are studying microwave engineering. The impedance, the voltage, the current is changing everywhere on the line. Okay? That's why we can design a microstrip line as a transformer, as a filter, as something else. Right? You guys, if you have experience, you use microstrip line, right? You can get rid of other things. Use only transmission line. And this one, you can make it like a resonator, it is like a transformer, or something else. Or become a capacitor, become an inductor. Use a transmission line. Because at high frequency, the voltage and current, they are changing. Actually, it's not only according to L, but also changing according to time. But we only look at the position, okay? We only look at the component of space. Okay, so what is this? We derived this one last week. Maybe you guys remember. I write down many things. I find you can find the details about how to derive these equations. Simply just put everything inside and do the simplification, right? Okay, so what is that? It is Z0 multiply Z0 plus J ZL tangent beta L, and then this is ZL plus J Z tangent beta L. Okay, and beta L, we can define it is the phase theta. It is only the phase contribution from the contributed by owning space. So beta L. Okay. And what is beta L? Think about what you have learned. Beta is 2 pi lambda g, or you say sometimes you use lambda. Why I always use lambda g? Because there are many lambda after all. We will talk about more about different transmission line of beta, but it's okay. Just write down lambda g. Lambda g is the wavelength. You can, if you have this relationship, you can find out that theta equals to 2 pi over lambda g multiply L. Okay? And those are important. So I write down them here. You need to be very clear about everything through chapter 1 until here. Okay? Everything is important. That's why we need a lot of exercise again and again. You miss something, you don't understand. You should not miss anything. Okay? Let me ask you one question. Can somebody help and draw me the function of tangent? Can anyone? Do you need an extra height? Do you want to draw the? Do anyone want the extra height? You can help me to draw the function of tangent. Anyone? Theta. Tangent theta. 1, 2, 3, 4. And this is 2 pi. Anyone? Raise your hand. Please draw it beautifully. Because the video is up. I mean, very beautiful. This is 2 pi. Are you sure? You can draw some line to help you to draw this. How about here? Those are also important. Yes. Okay. Okay, thank you. Basically, okay. Let me do some multiplication. Okay, you guys know this picture, right? About tangent theta. Why are we talking about tangent theta? Because I have tangent theta here and here. I need to know about tangent theta, and I can understand how my impedance changing. Okay, input impedance, how they change. So this is a figure of tangent theta. Okay, when your theta is 0, tangent theta is 0 as well. Let's write down. there are 4 spatial positions of theta. 0, and we don't know the value, but for this point, the tangent theta is infinite, either positive or negative. In this, it is pi over 2, and this is pi, and this is 3 pi over 2, and this is 2 pi. Okay, and let me write down. So theta it is 0 pi over 2, and this one pi, and pi 3 pi over 2, and pi. So tangent theta is 0, positive, negative, infinite, and also it is 0 again, and positive and negative, infinite, and 0 again, right? Okay. So can anyone help another bonus question? So what is L for these 5 cases? Anyone going into this question? What happened physically is the transmission line. What is the physical length of the transmission line? You will have your theta equals to 0 pi over 2 pi and 3 pi over 2 and pi. What is the physical length of your transmission line? Write down the ratio of that. How many lambda g, okay? Anyone help? Extra point. Anyone? What is the length of the transmission line? We will have theta equals to this 5 spatial number. Look at the equation. You can see that, right? It's not so hard, right? Anyone? Bonus, bonus. Write down that here.
最后一个检查一下。
Right. We must stay quiet. Sorry about that. Okay. Very good. Thank you for the correction. That's okay. So can see that there are only two cases. If the physical length of the transmission line, it is an even number, it is an even multiplication of 1/4 lambda. If it is an even number of the multiplication, you can write down like something like that. You can write down your length is something, it is an integer number, multiply the quarter wavelength if n is 0, 2, 4, 6, if it is even number, or if n is 1, 3, 5, 7, if that is an odd number. There are only two cases, okay? If it is even number, your tangent theta goes to 0, okay? If it is an odd number, the tangent theta is infinite, okay? There are only two possibilities of these 5 cases. Actually, there are more, right? Again, repeat again and again. Two different cases. For that case, it is a quarter wave transmission line or quarter wave transmission line plus the half wave transmission line times some integer. Or it is a half wavelength transmission line and the multiplication of this half wavelength transmission line. Understand? Okay. So for this one means 0, 2, 4, it is always maybe another number multiply the, this is another integer, okay? It is a multiplication of the half wave transmission line for this one, and then this one means your tangent theta equals to 0. And also, it is maybe another integer of it is, or another case is, it is a quarter wave transmission line plus the half wave length, the integer of the half wave transmission line, and where you can get tangent theta goes to infinity. Another possibility. So yeah, two possibilities. Okay? Because of this table and because of tangent theta. Okay? Okay, only two cases. So we look at only two cases. This is a case. Another case is and the others are just repeat again and again. Okay? Okay, so before we are taking a break, let me try to write down what we are going to discuss in the next class. We will discuss 5 different cases in the next class, okay? 5 different cases. The first case is what happened for here for your input impedance at the input end if your load is short. This is a case of load short. So this one is short. So Z error equals to 0. Okay, the first case we are going to discuss. Okay. Second case is what happened? You have short and open, right? If you know how to calculate short, open, load, let me write it down. Open. The third case is load matched. If your load impedance is your characteristic impedance, we call that match. Okay? So this is the third case. And the fourth case, and then the fifth case, D and the E here. So for that one, if theta equals to pi over 2, your L is theta pi over 2 lambda g over 4, and the theta is pi o theta it is pi, or your L it is lambda g over 2. The quarter wavelength transmission line or a half wavelength transmission line. Okay, so there are 5 special cases of our input impedance we are going to discuss after we are taking a break. Okay, let's take a break.